Hello, today we're going to be looking at applications and models of the trig functions we've been looking at. And just a little note for the notes today, I'm just going to round my answers to the nearest hundredth for the final answer. The first thing I want to review with you guys is a little bit about your angles of sight. We've talked about this before, and I know you guys did in geometry as well. But if you have a point that is above you, if you're looking at a point above you, like the top of the building, the angle that your line of sight makes with the line parallel to the ground is called the angle of elevation, okay? It's always measured based on the horizontal, okay? So if we have a horizontal, and again, if what you're doing is you're looking up to something, okay, that is your angle of elevation, okay? Your angle of depression is again measured from the horizontal. It says if you're at the top of the building, the angle between a line parallel to the ground and your line of sight is called the angle of depression. Okay, so again, always measured from that horizontal. Okay, that is our angle of depression. And those angles will have the same measure. Okay, so like if you had something like this, and we're looking at your angle of elevation, let me extend this a little bit, and you're looking at an angle of elevation versus the angle of depression. Notice those are alternate interior angles, so those are going to be the same anyway, okay? So example 1 says an engineer erects a 75-foot vertical cellular phone tower. Find the angle of elevation to the top of the tower from a point on level ground 95 feet from its base. Okay, so we have this 75-foot vertical cellular phone tower, and we want to find the angle of elevation to the top of the tower from a point on level ground 95 feet from its base. We're going to assume, again, it said it's a vertical cell phone tower. So we'll say they did a good job and it's a right angle. And again, if we're looking for the angle of elevation, we'll draw a triangle. And the angle of elevation will be from this horizontal to the top of the tower this way. Okay. And then we're just going to use right triangle trig to solve that. So if we set this up, we're going to say that the tangent of theta, because we have the adjacent and the opposite. So tangent of theta is our opposite over our adjacent. And then we're going to solve. Now, when we find the angle of elevation or angle of depression, I know that usually we had used radians when we use inverse trig. And again, if it's an inverse trig expression we're evaluating, we'll do that. But in general, we usually round these to the nearest hundredth of a degree. So in the mode in your calculator, make sure that we are in degree mode. And we know that in order to isolate the theta, we're going to try to do the inverse tangent. So I'm going to take the inverse tangent of 75/95. And I end up with about 38.29 degrees because I was in degree mode. That's it. I know you guys have done problems like that before. Okay. So let's spruce it up a bit. Example 2 says an observer in a lighthouse that is 350 feet above sea level observed 2 ships directly offshore. The angles of depression to the ships are 4 degrees and 6.5 degrees. How far apart are the ships? Well, let's try to draw a little picture to take for that. So here's our lighthouse. And again, here's the observer in the lighthouse. That's 350 feet above sea level. And it's talking about the angles of depression. And so the angles of depression, remember, are measured from this horizontal line. Okay. So one of them is going to be, let me take this color. All right. One of them is going to be 4 degrees, and one is going to be 6.5 degrees. So I'll have one go here, and then I'll have one go here, okay? Now, logically, so I have 2 right triangles that I'm dealing with. So logically speaking, if one has an angle of depression of 4 and one has 6.5, again, this is going to be the shorter of the 2. So that means that this is going to be 4 degrees. And then this part would be 6.5 degrees. Clearly not drawn to scale, friends, okay? I'll do this just to show you. Now, that isn't super helpful in each triangle, but remember that the angle of depression is the same as the angle of elevation. So that means that if this angle is 4 degrees, that this angle is 4 degrees. And if this angle is 6.5 degrees, then this angle is 6.5 degrees. So that's kind of nice that we have that. And notice that these 2 triangles actually do share this side. And again, let's assume that the lighthouse is vertical in comparison to those distances, okay? And so what we want to do is find the distance between the ships, okay? So here's one ship that's here, one ship that's here. What I'm trying to do is I'm trying to find this distance, D, between the ships. Well, notice that distance D is not part of, well, okay, it's part of the pink triangle, but it's not a complete side of the triangle. But I do notice that if I have this whole thing right here, this is the side of a triangle, and this right here is the side of a triangle. And if I knew the pink side of the side of the pink triangle, I could subtract off the side of this blue triangle to find that distance. So let me call this leg of the blue triangle X, and let me call this whole leg of the pink triangle Y. And I should be able now to set up some trig ratios because of those right triangles. I'll focus on the blue one first. So if this is 6.5 degrees, I called this X the adjacent. I know that 350 is the opposite. So opposite and adjacent, I can use tangent. So I can say that the tangent of 6.5 degrees equals 350 over X. Okay, cool. And let's set something up similar for Y. I can say that the tangent of 4 degrees is the opposite, which is 350, over the adjacent, which is Y. And you guys remember that these are numerical values. So like this tells me what X is and what Y is. So let's maybe solve for X and Y in each of those. I'm not sure if you have to do all the steps, but I could multiply both sides by X here, and then divide by the tangent of 6.5. And I can see that that will be an expression that would be equivalent to X exactly. Oops, I got my degree symbol. And I can do the same thing to this next equation. Y times the tangent of 4 degrees equals 350. So then Y is 350 divided by the tangent of 4 degrees. Now again, my goal was to find out how far apart are the ships. Well, we said that this distance was going to be this pink leg, Y, minus this blue leg, X. And so then I can take 350 over the tangent of 4 degrees minus 350 over the tangent of 6.5 degrees. I'm just going to put that in my calculator, you guys. I'm not going to find the decimals and subtract. So I'm going to take 350 over the tangent of 4 degrees minus 350 over the tangent of 6.5 degrees. And I'm in degree mode, so I don't have to mark it with degrees or anything like that. And then that's going to be my distance. My distance is about 1,933.32 feet. Okay. And again, here, because we were taking the tangent of 4 degrees, this is in degrees. We're looking for our distance. That distance is going to be in feet. Okay. All right, 1 sec. Okay. All right, more fun. Example 3 says a plane is observed approaching your home and you assume its speed is 550 miles per hour. You're just that good at estimating things. If the angle of elevation of the plane is 16 degrees at one time and 57 degrees 1 minute later, approximate the altitude of the plane. Okay, so here's you. Okay, and so you are approaching, you see that the plane is approaching your home. All right, so at one point, the angle of elevation of the plane, so again, the angle of elevation is going to go from the ground up. So at one point, it's 16 degrees. So let's say, okay, that at this point right here, that this is 16 degrees, and here's your plane. Okay. Then the plane again is approaching your home. So if it's approaching your home, it's going towards you. So now maybe let's say that the plane is here. And now we have that this angle is, mark it with something different here, that this is 57 degrees. Okay. And it wants us to approximate the altitude of the plane, which is how high the plane is. Now, here's the thing. We're assuming that the altitude is staying the same. So this altitude, the height of the plane when it started, is going to be the same as the height when you saw it 1 minute later. Okay. And we again have these two different triangles. Okay. One of them has an angle of 57 degrees and a height of h. This one here has an angle of 16 degrees and a height of h as well. So do we have anything that we can label other than h? Well, one thing that they both share is they both share this part. Maybe I could call this part x. And I could call this part y, except I'm going to be able to find out what that is. Because we know its speed is 550 miles per hour. And we know that this happened 1 minute later. And so if we think about what that little distance is going to be, we can say that our distance we know is rate times time. So that's going to be 550 miles per hour times the time, which is 1 minute. The issue are the units. We have 550 miles in 1 hour, but our time is 1 minute. And so what that means is that we're going to have to do a little conversion so that we can cancel. So the conversion is going to be how our hours to minutes. And again, we want to have hour in the numerator to cancel with this hour, minute in the denominator to cancel with that minute. And again, it's 1 hour in 60 minutes. So then I can cancel the minutes, cancel the hours, and I get that this is 550 over 60, which is 55 over 6 miles. So 55 6 miles. And that's what this distance is, because remember that it was approaching at a certain speed, and this was a minute later. Okay? So again, we have this speed, and that this is the change 1 minute later. So that means that this right here is 55 6 of a mile. And again, that's the distance that the plane is traveling in 1 minute. Okay. Well, now that we have that, we can set up our two equations, kind of like we did before. I'll focus on the blue triangle first. Again, I have tangent. So here I have that the tangent of 57 degrees would be h over x. And here I have that the tangent of 16 degrees, oops, sorry. The tangent of 16 degrees is going to be h over this whole thing, which is going to be x plus 55 6. Now, this problem gets much more obnoxious because it's not a nice number like 2, but that's okay. We can still get there, okay? Now, in the last problem we did, we were actually able to find some values, but we don't have that much information in the question. So we're going to have to use this system of equations. Now I noticed that again, h is the same. So let me isolate h in each of these. If I isolate h here, I can change this into the tangent of 57 degrees times x. And here I can turn this into the tangent of 16 degrees times x plus 55 6. And then that's also equal to h. And if each of those are equal to h, that means that they are equal to each other. So I can say that the tangent of 57 degrees times x is going to be equal to the tangent of 16 degrees times x plus 55 6. Now, remember, I know that these are numbers, but they're irrational numbers. The decimals get crazy. I'm going to preserve the integrity of the tangent of these trig functions. So I'm going to start by distributing. So I'll take the tangent of 16 degrees times x, and I'll take the tangent of 16 degrees times 55 6. Now think about it. We want to get all our x's together, so I'll subtract this. The tangent of 57 degrees x minus the tangent of 16 degrees x equals the tangent of 16 degrees times 55 6. Remember, these are numbers, so I can factor out an x, and that's going to be the tangent of 57 degrees minus the tangent of 16 degrees. And then I can isolate the x. I'll just divide. So in my numerator, I didn't say it was cute, is the tangent of 16 degrees times 55 6 all over the tangent of 57 degrees minus the tangent of 16 degrees. And then we can put that in our calculator. Now make sure we're careful when we do that. So I'm going to take the tangent of 16 degrees, close parentheses, times 55 over 6. But when I divide it, I want to make sure that all of this is in parentheses. So divide it by the tangent of 57 minus the tangent of 16. Okay. Again, the nice thing about the calculator is that you also could create a fraction this way. and then substitute the same thing in, the tangent of 16 times 55, 6. That's why I love this one. And then again, down here, you could just have the tangent of 57 minus the tangent of 16. Okay, and then we get that same thing. Okay, so again, just options depending on the type of calculator you're using. We can tell that this is going to be about 2.10 if I round to the nearest hundredth, but I'm just going to round on my paper because let's think about what we were looking for. What it wanted is this wanted the altitude of the plane. Well, x isn't the altitude of the plane. What's the altitude of the plane? H, okay? So what we're going to want to do now is find what h is. Of these two expressions for h, I think this one's a little easier. So I'm going to use the fact that h equals the tangent of 57 degrees times x. And I'm going to keep this number in my calculator and just basically multiply that by the tangent of 57 degrees. Okay, so my number is still in the calculator. I'm not chopping off decimals yet. I'm going to take this number and now multiply by the tangent of 57 degrees. Now I can round to the nearest hundredth because we were looking for h. So that's going to be 3.23. And the unit that we were dealing with is in miles. Okay. So again, it looks worse than it is. It's really just, setting up right triangle trig, to be honest with you, and then manipulating around, right? Okay, let's look at example 4. It says the ship leaves port at noon and heads due west at 20 knots or 20 nautical miles per hour. At 2 p.m., the ship changes course to north 54 degrees west. Find the ship's bearing and distance from the port of departure at 3 p.m. So there's a lot going on in this question. First, I'm going to draw a north, south, east, west grid, like coordinate plane to start, okay? And let's say that this is the port. Okay, so my original piece here is this port. My original origin is the port. And it does say that it heads due west at 20 knots or 20 nautical miles per hour. Okay, so when we're looking at what's happening due west, this is 20 knots. And then at 2 p.m., the ship changes course. So that means that from noon to 2 p.m., that is 2 hours. So that means that's going to be 40 nautical miles. So due west, and this is going to be 40 nautical miles. Okay. But at that point, the ship changes course. Excuse me, and the ship changes course to north 54 degrees west. What that means is that now I need to think about a new axis starting from here. And from there, I'm going to go north 54 degrees west. So again, from here, this is where we change course, okay? I'm going to go north and then 54 degrees west. Okay. And then that's going to be my new different piece that's here. And so this is basically my other direction. Now my other direction, I'm still going the same speed, 20 knots. And this is from 2 to 3 p.m. So that only happened for 1 hour. So that's going to be 20 nautical miles. So again, not drawn to scale. So again, this is 20. nautical miles. Okay? And what the question wants is it wants the ship's bearing and distance from the port of departure at 3 p.m. So again, this was the port, and we want to find out the distance and bearing from the port of departure. So from here to here, because this is where the ship ended up at 3 p.m. Okay. So again, this right here is where our ship is at 3 p.m. So it wants the bearing. Our bearing, I'll make green. Okay. So it wants our bearing, and then it wants our distance. Okay. The issue is we can't use right triangle trig because this triangle that we have is not a right triangle. I know. Okay. And I know that there's a right triangle that's right here, but we don't know what this height is, and it's only part of this distance. What I'm going to invite us to do is, again, make two triangles. What we're going to do is we're going to drop a, I'll do that in this color. I'm going to kind of like drop a perpendicular here to help us create those different triangles. Okay. So one of the triangles I'm going to use is this one right here. And I know that this is 20 nautical miles. Another right triangle could be this one here. I don't know what the heck these are, but I know that this is D, my distance. And then I know that this part of it is 40. If I had a name for this part, I could add that to the 40. So maybe let's do that. These share this side A. So I'll call this side A. And then this side B is part of this triangle. I'm going to have B and an extra 40 nautical miles. So this right here will be B plus 40 nautical miles. Now, this isn't very helpful unless we know some of our angles. Well, let's take a look at this picture again. Notice that we had the bearing of 54 degrees that was this way. You guys, aren't these complementary angles? So if this angle is 54 degrees, I know you can't read that, but that's what that says. So this 54 degrees is really what this angle is measuring. Then what would this angle measure? We could take 90 minus 54, and we get that this angle measure is 36 degrees. And the reason that that's helpful is because if we know that, then we can set up some trig functions with that. We could say, for example, that the sine of 36 degrees is our opposite A over our hypotenuse 20. And we could also say that the cosine of 36 degrees equals our adjacent B over 20. Okay. And that means that we have measurements for A and B. That A is the same as the sine of 36 degrees times 20. And that B is 20 times the cosine of 36 degrees. Okay. And again, it doesn't look like it to us because it has those trig functions, but these are actual values, you guys. These are actual numerical values. So now we know how big A and B are. Okay. So when we're looking at that, as far as this triangle goes, because again, the question wasn't asking for A and B. What it's asking for is it wants the bearing and then the distance. So one of the things that we could do is find what this angle theta is, because we know what, and I'm going to call this theta, okay, I'll color it with the purple again. We could find this angle theta because we know what A and B are. So for example, I could say, all right, I know that the tangent of theta equals A over B plus 40. Okay. And I know A and B. Now I know that A is 20 times the sine of 36 degrees. And I know that B is 20 times the cosine of 36 degrees. So then I can add 40 to that. Okay. So then to find my angle theta, I'll take the inverse tangent of this whole thing. So I'm going to take the inverse tangent of this expression that we've set up. And that can help me find my angle theta. So in the calculator, I can take the inverse tangent, and I'm going to take 20 times the sine of 36 over 20 times the cosine of 36 plus 40. Oops, I didn't need that there. Okay. And I get that theta is about 11.82 degrees. And you might say, okay, Mackie, that's going to be my bearing. But remember, the bearing isn't measured from the horizontal. Our bearing is measured from the vertical. So remember that the bearing that we had talked about would be this angle that's right here. So if this angle is 11.82 degrees, then what could we do to find this angle? So for the bearing, we could just take 90 minus 11.82. And we can see that that's going to be 78.18 degrees. Now, when we give bearing, what we like to do is we like to give it in north, south, east, west, right? So this would be a bearing of north 78.18 degrees west. So again, this is north. And then we went 78.18 degrees west. So this is our bearing. Okay. Then the other thing that we would need is we would need this distance. So we have a couple options at this point. We could use the Pythagorean theorem with these A and B values if we wanted, or because we have this estimate that's in our calculator right now for theta, we could use that as well. If I look at this angle right here, using A and D might be easier. So I could say, all right, let's use the sine of theta equals A over D. So I know that the sine of theta equals sine of, 20 times the sine of 36 degrees over D. So D times the sine of theta is 20 times the sine of 36 degrees. So my distance would be 20 times the sine of 36 degrees over the sine of theta. And remember, my sine of theta, or my theta, I should say, was about 11.82 degrees. Okay. So, I mean, I guess I could store that. So I could store this as x, okay? And then I'm going to take 20, oops, let me use this again. Oops, 20 times the sine of 36 degrees over the sine of that angle, oops, of that angle x. And so I get about 57.40. If you use the rounded answer, so if you took 20 times the sine of 36, and then you divided by the sine of 11.82, notice that it's pretty close, but so the hundredths rounds a little bit differently. So since we stored that value, so I'll make a little note that this is from the calculator, then we can say that our distance is going to be about 57.40. And again, the distance in this case was in nautical miles. And then that would be our distance. Okay. This is a lot, probably not on a quiz or test situation, just to be honest with you, but it's really good to see these different relationships and be able to look at the different triangles, dissect them, see how they interact with each other, etc. Something like this does have the bearing in it as well. Okay. All right. The last thing is this idea of simple harmonic motion. And if all goes well, I've talked to you about this already, but if not, here we go, it's in the video. So simple harmonic motion is used to describe the motion of a point on an object that vibrates, oscillates, rotates, or is moved by a wave motion. When we have like a weight dangling on a spring, going up and down is an example of this kind of motion. Basically, the type of simple harmonic motion we're going to deal with is going to be either with sine or cosine, because those are those types of wavy periodic functions. And we do not generally have translations. Okay, so notice we don't have any horizontal shifts or vertical shifts. We're just dealing with a difference here with A. And then instead of B, we have this little omega type of a thing here. Okay, so the things that we're really looking for here are, when we write the equations, are we want to find A and we want to find omega. So what do these different things mean? So what D represents is D represents our distance that the object is at. T represents the time. And A and omega are real numbers. Per usual, you guys, our amplitude will be the absolute value of A. Now, when we were dealing with the trig functions, you guys, we said that our period was 2 pi over B. Well, here our B has been replaced with omega. So our period is going to be 2 pi over omega. Now, when we talk about the frequency is how many cycles per second it is. So if the period is the time it takes to complete one cycle, the frequency is going to be the reciprocal of that. So the frequency is going to be omega over 2 pi. Okay. So our amplitude is the maximum displacement, which means the maximum that it moved from where it started. The period would be the time to complete one cycle. That'll be 2 pi over the omega. And then the frequency is just the reciprocal of the period. The other thing is you have to decide whether you're going to use sine or cosine. And if your displacement at t equals 0 is 0, what that means is that you want basically it to start at 0, 0. Which of those trig functions starts at 0, 0? Sine or cosine? Sine. So that means that if we have a displacement of 0 when t equals 0, we're going to use sine. So example 5 says to write the equation for the simple harmonic motion that satisfies the following. First, we have a displacement, t equals 0 is 0. The amplitude is 4 centimeters, and the period is 6 seconds. So first, again, let's write the equation for this. Well, this displacement, t equals 0, it's saying that it's 0. What that means is that we're going to use the sign, because its displacement, it had no displacement when we started. Okay. The amplitude of 4 centimeters tells me that I'm going to use that A equals 4. And the period of 6 seconds means that I can say that 6 equals 2 pi over omega. And then I can try to find what my omega is. We can solve. So I have 6 omega equals 2 pi. And so omega equals 2 pi over 6, which of course we're going to reduce to pi thirds. And we're going to put those in. We know what trig function to use. We know what A is. And we know what omega is. And so then we can put that into our simple harmonic motion. So we're going to say that D equals 4 times the sine of pi over thirds times t. And technically we don't have to have that in parentheses, but we'll keep it there just in case anyone gets confused. So that's my equation. It's not too bad. Now it says, what is the frequency? Well, again, the frequency, we know that the period is 6 seconds in 1 cycle. So that means that the frequency is going to be the reciprocal of that. It's going to be 1/6 of a cycle per second. So legit, we just take the reciprocal. Okay. Alrighty. Last one, example 6. Here they give us an equation for simple harmonic motion. D equals 6 times the cosine of 3/4 pi times t. A, it wants the maximum displacement. Well, we know the maximum displacement is going to be that A value. So because A equals 6, our maximum displacement is going to be 6 units. Because they didn't give us a unit. Okay. B asks us for the frequency. Well, we can tell from the equation that our omega is 3/4 pi. And we know that the period is 2 pi over omega. So I'm going to take, oh shoot, it didn't want the period, it wanted the frequency. So for B, we want the frequency. So the frequency is going to be omega over 2 pi. So we're going to take omega, which is 3 pi fourths, over 2 pi, which is the frequency. And we could do a couple things, however you want to simplify this fraction. You could start by multiplying by 4/4 to clear the to clear the complex fraction. That gives me 3 pi over 8 pi. Cancel the pi's. That gives me 3/8. So that's going to be my frequency. So 3/8 of a cycle per, it doesn't give us a unit, so per unit of time. Usually it's in seconds. But that would be our frequency. Letter C, let me read this one first. It wants the value of D when t equals 4. So we're just going to let t be 4 in this equation. And so this means that we're going to evaluate 6 times the cosine of 3 pi. I'll evaluate the cosine of 3 pi. Hopefully we don't need to draw, but if we do, so 1, 2, 3 pi, I can see that that's going to be -1. And so that would give me -6 units. And then finally in letter D, it says the least positive value of t for which d equals 0. So again, let's let d equal 0, and we're going to put 6 times the cosine of 3 pi fourths t. And let's solve for t. So we can divide by 6. So I get 0 equals the cosine of 3 pi fourths t. And essentially, I want to try to find what t is. And so right now, let's just think about this. When is the cosine of theta equal to 0? Okay. One of the smallest values is when theta is pi over 2. And when we look at what theta is here, this is our theta. Okay. So then what we're really saying is that 3/4 pi t has to be equal to pi over 2. Because again, we want that value to be equal to pi over 2. So I could multiply both sides by 4. So I get 3 pi t equals 2 pi. And then divide by 3 pi, and I get that t equals 2/3. So it'll be 2/3 of a unit of time, which probably would be seconds, but I didn't give a unit, my bad. Okay, and so that's a little bit about harmonic motion. Extra practice to follow. Okay. That's it. You guys, let me know if you have questions. Have a great day.